In this section, we go through the molecular orbital diagrams more quantitatively to understand how much the band gap is going to be due to covalent bonding as opposed to the electronegativity difference between the atoms. We have been describing the bonding and anti-bonding wave functions as a linear combination of the atomic orbitals of the two atoms that make up the bond. For example, in the hydrogen molecule, the bonding wave function is approximated as the sum of the atomic 1s orbital around one of the atoms plus the atomic 1s orbital of the other atom. The two atomic orbitals are combined in phase, here shown as both atomic orbitals being positive. That leads to constructive interference in the region between the two atoms. The antibonding molecular orbital is also a linear combination of the two atomic orbitals, but this time the phase is opposite, leading to destructive interference in between the two atoms. In the diatomic molecule, the energy of the bonding molecular orbital is lower in energy than the atomic orbital of either atom, such that when there's only two electrons in the diatomic molecule, there is a net reduction in energy. Here we will solve for the general case of a molecular orbital made up of a linear combination of two atomic orbitals, where these two atomic orbitals might be of different atoms. Here, C1 and C2 represent the magnitude and phase of the constituent atomic orbitals. The Hamiltonian for our wave function contains the kinetic energy operator, but in addition we have two potential energy operators, one for each of the atoms. We can think of V1 as being the Coulombic potential of atom at site 1 and V2 as the Coulombic potential of atom at site 2, where the sum of them is the Coulombic potential for the molecule. To solve this problem, we will use properties we already know about the atomic orbitals so that we won't have to do any integrations or derivatives. For example, we know that each of the atomic orbitals, where I could be either atom 1 or atom 2, such that psi star psi of the same atom equals 1. For the Hamiltonian operator, we will consider how it operates on each individual atomic orbital one at a time. For example, when the Hamiltonian operator is operating on wave function I and then will be multiplied by wave function I star, we will call that H sub II. In this case, the Hamiltonian operator operating on a single atomic orbital has the same two components of the Hamiltonian operator that we had from the hydrogen atom, which will give us the energy of a hydrogen atom. In comparison, the potential energy due to the other atom is small. Thus, H psi I is equal to E psi I, where now E is just the numerical value for the energy. We can pull that outside the integral and simply get the integral of psi star psi, which we know to be 1, such that this integral is approximately equal to the energy of that atomic orbital. There are times when we will need to do the integration of two different atomic orbitals, such as psi on atom 1 star times psi on atom 2. We call this the overlap integral given by the value s, where we know that the overlap between the two wave functions is small. The other integral we will need will be the Hamiltonian operating on one of the atomic orbitals times the complex conjugate of the other atomic orbital. We call this integral the exchange integral and denote it as Hij. Now, due to the symmetry of the Hamiltonian operator, H sub ij equals H sub ji. We will show in the next slide that the exchange integral is the energy of the atomic orbitals averaged times the overlap integral plus another term we call the bond integral. Then we will show that the energy of the bonding molecular orbital is the energy of the atomic orbital reduced by an amount proportional to the bond integral. Now keep in mind that many of these values are negative. For example, the energy of the atomic orbital is negative, and so is the energy of the bonding orbital, so that the bond integral itself is also a negative value, reducing the energy of the bonding orbital. The energy of the antibonding orbital is also relative to the energy of the atomic orbital, but this time it's raised up by an amount proportional to the bond integral. The small positive overlap integral is such that it slightly reduces the amount of bonding and increases the amount of antibonding, such that the net increase of the antibonding orbital is greater than the decrease of the bonding orbital. Here we will evaluate the exchange integral, keeping in mind the properties that we discussed on the previous slide. Here we will take the symmetry of the Hamiltonian operator as a given. Although quite plausible, it's a bit complicated to derive it. To evaluate the operator Hij, we take the full Hamiltonian operator operating on one of the atomic orbitals, psi j. The Hamiltonian operator contains the kinetic energy operator plus the potential energy operator of atom 1 and the potential energy operator of atom 2. Plugging this in, we have the kinetic energy operator operating on psi j, the potential energy operator of its own atom on psi j, and then the potential energy of the opposite atom on psi j. The first two terms we recognize is simply the Hamiltonian of atom j, such that we know that that equals the energy of atom j times psi j. Because this energy is now a numerical constant, we can bring that outside the integral, giving us the energy of the atomic orbital at j times now an overlap integral s. Then we have the potential energy function of one of the atoms, but the wave function of both of them. Using now the symmetry of the Hamiltonian operator, we get a similar equation for Hji, where this time we have the energy of the I wave function and the potential at j. If we now sum these two equations and take the average, we get that Hij equals Hji is the average of the energy of the atomic orbitals times the overlap integral. And then we have a symmetric potential operator, which we call the bond integral, operating on either of the two atomic orbitals. We will simply denote this bond integral as Vij, such that the exchange integral equals the average energy of the two atomic orbitals times the overlap integral plus the bond integral. To solve for the two coefficients C1 and C2, we will need two equations. For each of the equations, we will consider the Schrödinger equation as an operator operating on the full molecular orbital projected in one of the atomic orbital directions. Distributing through the molecular orbital as a linear combination of the atomic orbitals, we get four terms. The first term comes from the Hamiltonian operating on psi 1, which we know to be approximately the energy of the atomic orbital 1. The second term is the energy of the molecular orbital from the Schrödinger equation that we are solving for. So we bring that outside the integral and leaving us with psi 1 star psi 1, which we know equals 1 from the normalization condition. Now operating the molecular orbital on psi 2, we have the Hamiltonian operator operating on psi 2, which we know to be the exchange integral H12. Then the energy of the molecular orbital we are solving for is in the equation here, where we can again pull out a constant and we see we have the integral of psi 1 star psi 2, which we know as the overlap integral S. Since this part comes from the Schrödinger equation, H psi molecular orbital equals E times psi molecular orbital, that should be 0, meaning this equation should also be 0. So we'll keep that equal to 0 here and here. Collecting terms of C1, I have E1 minus E times C1, and collecting term C2, I have H12 minus ES times C2, all equal to 0. I can now produce another equation using psi2 instead of psi1 as before, and this simply changes all the 1's to 2's and the 2's to 1's. Thus, I now have two equations for my two unknowns, C1 and C2. Using linear algebra, we can write this system of two equations and two unknowns in matrix form. In this matrix form, this equation can be easily solved by a computer or calculator, and as we get to more complicated problems, we'll see that the matrix form is essential for solving the problems. The solution to this matrix equation will give us the solution to the Schrödinger equation for the molecular orbitals. For the bonding and antibonding molecular orbital energies are given by the average of the atomic orbital energies of atom 1 and atom 2 plus or minus some difference. On an energy diagram, let's call the atom with a higher atomic orbital energy as atom X and the atom with the lower atomic orbital energy as atom Y. This difference in atomic orbital energies, which we call the quantity 2A, is due to the difference in electronegativity of the two atoms, with Y being more electronegative, being more happy to accept electrons, and X being more electropositive, being more happy to give electrons. The energy of the bonding molecular orbital will be lower in energy than the electronegative atomic orbital by an amount we call B, the bond energy. Similarly, the antibonding molecular orbital will have an energy higher than that of the electropositive element's atomic orbital by an amount approximately equal to the bond energy B. These two bond energies are the same when we ignore terms of the order of the overlap integral S, so we approximate S equals 0. The gap then between the antibonding and bonding molecular orbitals is given by 2A plus 2 times B. The solution to the matrix equation then gives us the energy of the states, or gives us the energy of the bonding interaction in terms of the interaction energy V, here V12, and the difference in energy between the two atomic states, A. Thus, the reduction in energy due to bonding, or B, depends not only on the interaction energy from the quantum mechanics, but also on the difference in energy between the two states to begin with. Larger separation of the atomic orbital energy states gives us a smaller bonding interaction. This tells us that the bond energy is largest when A is 0. A is 0 when the electronegativity of the two atoms is the same. When X and Y are the same atoms, the bond energy is exactly equal to the bond integral V. If we then solve for the constants Ci, we will see that they are proportional to the energy difference between the atomic orbital and the molecular orbital in question. This means that the bonding molecular orbital has more character like the more electronegative atom or anion, whereas the antibonding orbital has more character like the electropositive atom or the cation. In the case where X and Y are the same atoms, we get C1 equals C2, or equal contribution from both atoms. In summary, when two atomic orbitals mix, the state of higher energy, or the cation state, rises in energy to form the antibonding molecular orbital, whereas the state lower in energy, or anion state, reduces in energy to form the bonding molecular orbital. To a first approximation, the bond energy is due to the reduction of the anion state, which will be filled, and this reduction is about the same as the increase in energy of the cation state to form the antibonding orbital. The bond energy B is less if the two states already started off very far apart in energy. The gap between the bonding and antibonding molecular orbitals is due to both the bonding as well as the ionicity between the two atomic orbitals, or the energy difference to begin with of the two atomic orbitals. The bonding states have more character closer to the anion states than the cation states, while the antibonding states are closer in character to the cation states. One can also consider this effect as due to the polarity or ionicity of the bond.